Good afternoon, everybody. We're so glad to see that so many of you decided to listen to our talk. Just a quick heads up that there has been a change in the title, so just that you know, today we'll be talking about neural architecture search. My name is Jelena. I'm a customer engineer at Google Cloud, and I'm focusing on data analytics and machine learning. And I have Chris with me. Chris?
Hi, I'm Chris. I'm based in Munich. I'm a cloud space architect focusing on machine learning, and that's why we brought this beautiful new title and the beautiful new agenda to you today, because it's way more interesting than just data.
All right, let's look quickly about the content. So our talk will be short and crisp. Nevertheless, we want to explain what NAS is, to explain you a little bit the building blocks so you can understand how the technology works. And Chris is going to talk more about the power of NAS. So why is it really a good technology to use? And we will tackle some real-world use cases, some of our customers and ourselves that have been using NAS. And we're going to wrap up with a short summary. Before we start, I would like to know, are you familiar with NAS? Just like raise your hand if you are. If not, I'm not going to bring you to the stage. No worries. It's all good. No. All right. Okay. You will have a lot of things to learn in the next 20 minutes. So this talk will actually explain a little bit about the motivation, why NAS technology. So our Google Brain team back in 2007 recognized that we need a better approach in terms of scaling and designing machine learning models. And they thought, like, can we build an algorithm that can design a novel a neural network architecture that can outperform the handwritten ones? That will help us, Google internally, as we use a lot of machine learning models in production, and also to the broader community to build faster and better neural networks based on the metrics that you select. Why? We all know that neural networks are really flexible and powerful for many different use cases. But still, even for us, so in production, we have a lot of experienced machine learning engineers and data scientists that build these models. And nevertheless, it takes a lot of time and takes a lot of tuning, a lot of effort, and of course, expert knowledge to build them. So what is it? So it's basically a technique for automating the design of artificial neural networks. As mentioned, they can go from very simple architectures, but more often, especially for some complex use cases, such as autonomous driving, for example, that can really be, let's say, challenging in terms of that 10-layer network. You can imagine how many different architectures we're talking here that you can select from. Where does it belong? For those who are familiar with machine learning in general, you probably know that there is a concept of AutoML that basically where on GCP you can build or actually you can train your models on already pre-built. You can train your models with your data with pre-built models, and NAS is actually subfield of the AutoML. And if we look at the hyperparameter tuning, that actually belongs like hyperparameter optimization is a subset of NAS. So with NAS, the whole idea is to find optimal architecture and also to find best hyperparameters. Talking about how it all started, so I mentioned Google Brain team back in 2017. So they published a paper, and they have been using these two data sets that in both cases they developed NAS actually as an algorithm, developed basically a network architecture that outperformed hand-coded architectures. And you can see here in terms of test error rate, the improvement, and also almost 0.9% faster, so one time 0.05 times faster than the previous one that used a similar architecture. And the same was with Pentree dataset as well. And from there, if we look what NAS has contributed in terms of like different benchmarks, here we see image classification benchmarks. So we can see some of the state-of-the-art neural network architectures that kind of performed much better in terms of here the metric was accuracy than the hand-designed ones. Where does NAS sit in your machine learning development flow? So if you see the whole flow from generating the data, labeling the data, and building and training the models, that's where NAS sits, in the actual training part. In the training part, Chris will explain how the process works in more detail, but the whole idea is to search for the optimal architecture for either for the particular metric, such as latency, memory, or power, or even combination of them. And here you see how we think as Google about this AutoML and NAS in general. So obviously, we work with a lot of smart people, with smart customers, and the idea is everybody has a lot of experience, but in reality, we all spend a lot of time in bringing our machine learning models, finding the optimal architectures and hyperparameters. But you can do this also from scratch with NAS. The idea is that you don't have to build them from scratch. Of course, there are some, let's say, human interaction, some things that you can select, but obviously that process is rather simplified. And it sits, we have NAS within our Vertex AI platform, so our end-to-end machine learning platform, as one of the offerings that we have for deploying and building your machine learning models on GCP. Let's look in the building blocks. That's very important to understand before Chris goes into how the technology actually works. So we have 4 important building blocks for you to understand in order to better understand how actually the technology works. So we have search spaces, we have search strategy or model generator, we have search algorithm and model of evaluation that we are all familiar with. Search space, in a simple language, is actually your use case. So search space defines the type of neural networks that will be designed and optimized. And of course, as I mentioned before, and you will see later, we offer pre-built search spaces and custom ones so that you can basically select based on your use case. Search strategy, or as I prefer to call it, model generator. So what it actually does is samples the number of, let's say, proposed network architectures without actually constructing it and training it. From there, we have a search algorithm that receives these different child model performances metrics as rewards. So as I was mentioning before, you can choose accuracy, latency, memory, custom metric too as well. And then the idea is to optimize the performance of these architecture candidates. And finally, we have model evaluation that we evaluate our NAS model against evaluation validation data. So within search spaces, we have pre-built ones, and here you can see the example ones that you can select already. But nevertheless, if your use case is a little bit more custom than this, then you can use the custom search spaces. And for that, we have PyGlove, that is lightweight Python library that can be used for using your for designing your custom search spaces. And that's we published already on GitHub. And with that, I'll let Chris to explain you how it works.
Thank you very much, Jelena. So, how does it work? You've just seen the theory of NAS, you've seen the building blocks, and ideally you know or have an idea how this all should come together. So it's actually, it feels fairly simple. And I think it's so simple that it's actually revolutionary. And we are kind of stupid how we did it in the past, to be really honest with you. So back in the day, it was always, whenever you took a machine learning course or you got to your professor, it was always the question, how do I tune my hyperparameters? That was stage one. And they were always like, yeah, you're not an expert, you should like try and figure it out by yourself and maybe iterate through it. And it seemed fun to do that. Obviously, you're gonna do and improve on that. You build a really nice model by the end of the day that you think is state of the art for your knowledge. However, your knowledge is like fairly limited, or at least my knowledge in the machine learning space, so that I'm not able to outperform an entire machine learning team. However, having like a simple feedback loop might solve that problem. So the paper that Jelena mentioned is from 2017. You can look it up. It's free to access for everyone. And it has like a really simple architecture. So we use a recurrent neural network where a controller sits on the left side. We have a so-called child network on the right side. And the idea is pretty simple. So basically, controller is using a search space, whether it's like a custom search space or like a predefined search space. These search spaces, I'll tell you in a bit what they are actually capable of. But however it starts, you pick a search space, you let the controller define an architecture based on the search space. This defined architecture is called the child network. This child network in the paper was like trained for accuracy. So we got a result out of it. We used reinforcement learning to basically feed in the result of the accuracy back to the controller and saw how we did. So based on the parameters that we used in order to design the child network, we can basically then, or we did use for accuracy, which is unfortunately non-differentiable, we used the policy gradient to update the parameters and reiterated that process. So just building a network out of the search space that becomes better and better. So this is the theory. So in words, that's actually like fairly simple how it started. So we have a controller. It uses hyperparameters, and hyperparameters, as you might know, are like parameters within the networks, but we see the hyperparameters as the networks themselves, so also the layers and the individual building blocks. So the child network is generated, and that's the beautiful part. The reward metric is not only accuracy. It was on the paper because it performed really good. However, you are capable of choosing a reward metric for the reinforcement algorithm by yourself. This can be accuracy, this can be latency, memory, or combination of those. And this is really important because on every other industry, you do have a different focus. And we're gonna see real use cases by the end of the presentation. Then we have the policy optimization, which I mentioned is under uncertainty because we used accuracy here. It's non-differentiable, but you can adjust the policy gradient then. And we do basically do 3 computations. Prior, we do an estimation of the child network to see how does it perform, how do we think it performs. Then we build it, we perform how it, or we evaluate how it really performs, we get the accuracy out of it, and then we adjust the policy gradient. So that's the theory behind it. So how does it work? And it's fairly simple, as you might think. And this is what I really like about NAS, the power of it. It goes more in the direction of artificial general intelligence, because now we don't build a neural network to solve a problem. We ideally build a neural network that can build neural networks to solve problems. So like one step prior to that. So this is like a nice animation that we published in the blog post. And you can basically see, this is the search space that we have been using. So they're convolutional layers, deconvolution layers, multi-head attention layers, some activation functions. And this is like the search space where the algorithm can pick from. And we designed neural networks based on the search space. And as you can see, when you iterate through it, it basically has a lot of possible layers or segment building blocks, however you want to call them, to pick from in order to improve like on a certain parameter. And by a number of iterations that you are able to define, because it's a custom metric, you can basically see how it improves over time. And when you're satisfied with the accuracy, you can basically export the model and use it from there. So these are the hyperparameters that you might know. We've just seen the building blocks, like convolutional layers. Within those convolutional layers, obviously, they're like the hyperparameters that you know from hyperparameter optimization. And these will be automatically adjusted by the NAS algorithm as well, like number of filters, filter height, filter width, stride height, et cetera, et cetera. And you can feel that outperforming an ML expert team is like fairly more easy with an algorithm because there's so many different parameters you can tune and might tweak, and having an algorithm to do that is better than just like a number of human beings. So this is when you deploy it, basically, how it looks like. Defining the search space. You have the search strategy that I was mentioning, or the model generator that generates the child networks, and you have the child, which you evaluate then, and then it goes back. So this is like, okay, if we can do that for one child network, it's actually fairly simple to do that with multiple child networks, ideally at the same time. So we don't need to wait, and you know machine learning problems that can run for weeks and weeks of training. Ideally, we have like a better compute power, but the power of it, you can now basically build hundreds of child networks at the same time and let them train, define the number of epochs, how often do you want to iterate through them, and get the feedback back of the best model and just build on this one. So we're having lots and lots of child networks, and we like those best, and basically we feed from there and improve for the model metric that we are actually looking for. So some theory behind it is obviously from the paper here, we work with probabilities. It's an autoregressive controller, so we basically predict the hyperparameter one at a time. And the beautiful part that I mentioned is the training speed, because you can accelerate your training with parallelism and asynchronous updates. So basically what you do, you spin up a container, put the child network in, let it train. When it's finished, basically you can use the container for either another child network or get rid of it. So there's a lot of compute involved, obviously, but the main idea here is, okay, we spend a lot of time in training, and obviously a lot of resources because a lot of iterations, but the end model itself needs to be like a little bit better than what we could do by handwritten code or handwritten engineers, so that we can save later on, whether it's energy or whether it's like, for example, the car example, that we can avoid crashes. So the power of NAS, and I only have like four minutes left, so I need to hurry up, but there's so much to speak about. Anyway, the power of NAS, like in a nutshell, if we try to sell it, I think it's nothing that we actually want to sell in terms of, I think it's a no-brainer, and there's no idea why no one should use it. So NAS can obviously outperform handwritten models, or at least it is on par, so you don't need the ML engineering team with the expert knowledge to design it. So there's no preparation needed. And as I was mentioning, or Jelena was mentioning, it's of 2017, so it's fairly new research. So research grows quickly, but as of right now, it's not totally independent of human bias because you need to pick the search space, right? Going a little bit further on that idea would be actually getting rid of all the search space and let another neural network design the search space for you that the NAS algorithm can pick from. So the white search bit as of right now is the hyperparameter optimization, the structure itself, and the building blocks. The reward signals we have seen. And this is just one example that I found really beautiful. So we have R50, which is a hand-coded image detection algorithm for 2D images. And this is like really good. It performed like with an average position of 37. And for one iteration, it needed almost 100 billion flops, so 100 billion floating point operations, to do a fairly good in the data set and a fairly good average position. So this is like R50, as I was mentioning. We did the same thing with the NAS-coded model. We found, obviously, we did a really good or better precision here, like almost over 5%, and at the same time decreased the number of floating point operations, so we are more energy efficient and more precise. And now look at that. It's fairly difficult to build this from scratch, right? Because you see not only the different layers that are structured in a different order than to the traditional convolutional networks that you know, but also we have a lot of skip connections. And you see that there are so many possibilities you could choose from, and NAS does that for you. So that's the example. And we can not only do this for 2D image detection, so especially in vision, we are on the forefront of using NAS networks. So there's a lot of classification models. There are image detection models, so basically the boundary boxes around the image, and even image segmentation, where NAS outperforms handwritten models today. Real-world use cases in 1 minute. Okay, that's going to be exciting. So we have autonomous vehicles, and you can think of like Waymo, for example, which I'm going to say in a second. And there's, for example, there's accuracy, and latency is really important because you want to avoid the crash, right? And you want to avoid evaluating whether this is a car or a human being on the street. So we have like medical imagery, satellite, hardware. Waymo, it did really good. This seems like fairly simple, this model, but you can also see the skip connections that we use in the different layer types. So we reached like 20 to 30% lower latency with the NAS network and 8 to 10% lower error rates. And this is revolutionary. So this is our beautiful case from the automotive industry that Waymo uses. Same thing in your phones for the Pixel one. So we can basically do with a TPU on the Tensor chip on Pixels, we have also a built-in NAS model that basically uses machine learning to unblur faces, for example, or to refocus the image afterwards. That's already in production, and maybe you use it every day and you didn't even recognize that it was built by NAS. Another example is BERT, our famous natural language processing model. There is now a mobile version of BERT out there built by NAS that's way, way smaller than the previous build version on edge devices. Why does it need to be smaller? Why is it cool that it's smaller? Because you have like a lower latency when you get the response back, especially when you do like translations and stuff. That really comes in handy. Summary. Oh, I'm over time. Summary. Anyway, we design new models from scratch, basically just giving the search space. We can do better than handwritten coders. We are faster with it. And obviously, you still can tweak parameters. How many child networks do I want to deploy, for example? With that, and that's the key that the 2 sentences I want to give you away with, is like use NAS. You can use it actually not only to improve accuracy, but the major part of it, what we see at a lot of digital native companies, for example, the deployment process time decreases because you don't need to staff an ML team and you don't need to spend weeks and weeks training the network because the algorithm does it for you. With that, 21 minutes, I think we're going to the next call. It's Jay. So thank you for being here, and I hope NAS was kind of interesting and stay forward looking good. Thank you.